Hey folks, we're back with another video covering topics in the SOA's Statistics for Risk Modeling exam. Today's video covers the bias-variance trade-off. Variance and bias are two important concepts in statistical modeling that help us understand how well a model fits the data. Let's look at a simple example. We plop some points down, plop, 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 and fit them with a linear regression line. What are some ways we can determine if a model is a good fit? In a previous video, we talked about the mean squared error for a single data set. But what if we want to know how stable the model is across data sets? That's where bias and variance come in. Simple models like linear regression have low variance, meaning if we change the data slightly, the estimated line wouldn't fluctuate much. If we draw a slightly different sample of data, notice how the new linear fitted line still looks very similar to the original. This indicates low variance, since the model is stable across different data samples. Second is bias. Bias is a measure of how far off our predictions are from the actual values. Linear models typically have high bias, meaning they oversimplify the relationship. The estimated line doesn't actually represent the actual values for many of the points. Okay, so looking at the linear line, it has low variance, it's stable, but it's missing the point. Literally, it's not going through any of the points. It has high bias. What if we play connect the dots? Look at that wiggle, the errors are gone. This is terrible. We have low bias now, sure, but this squiggle has massive variance. Let's see this in action. Watch what happens when we draw a slightly different sample of data. The curve completely changes. That is high variance. Complex models are more likely to have high variance, meaning if we change the data slightly, the fitted curve would change a lot. But to be fair, they do manage to hit the targets. So the question is, do you want a stubborn line that misses the point, or a fickle squiggle that can't make up its mind? That, ladies and gentlemen, is what we call the bias-variance trade-off. All right, so we understand that the trade-off between bias and variance is crucial for building models that generalize well to new data. But here is the problem. Typically, as model flexibility and usually complexity increases, bias goes down, but variance goes up. And if you decrease flexibility, then bias goes up and variance goes down. So, high bias, low variance? Those are usually simple models, like linear regression. They're stable, but they might miss the pattern entirely. That's called underfitting, because it doesn't do a good job of fitting the training data. However, it may generalize well to new data. On the flip side, low bias, high variance, these are complex models, like deep neural networks. They capture the pattern well, but they're way too sensitive to noise. That leads to overfitting, because it overfits the training data and may not generalize well to new data. The optimal model is the one that finds a balance, essentially minimizing the expected test MSE. The expected test MSE is equal to the sum of the squared bias plus variance and irreducible error, which is the noise in the data that cannot be explained by any model. So if you look at this table, you can see that low flexibility and high flexibility models both result in higher expected test MSE. Generally, models that minimize the expected test MSE find a balance in the medium flexibility range. All right, so let's look at the decomposition of the expected test MSE in terms of formulas. Imagine we have a specific value of interest, x0. The expected test MSE formula is shown here. It equals the variance plus the bias squared plus the irreducible error. The bias is squared to make sure all the terms are positive and on the same scale. Now, let's break these down. First, we have variance. This is a measure of the squared fluctuation of the estimate around the mean estimate. If it changes a lot, you have high variance. Next, we have bias. This measures, on average, how far the predicted value is from the true relationship between x and y. For example, if the actual data follows a curve and the model is a straight line, the bias will be high. And finally, the irreducible error. This is the noise in the data that cannot be explained by any model. If you're interested in the derivation, here are the steps to decompose the expected test MSE into bias, variance, and irreducible error. However, This is far beyond the scope of the exam, so you can skip this section if you want. The first thing to note is that the observation value, y0, equals the true function of x0 plus epsilon. The true function represents the underlying relationship between x and y, and the error term represents the random noise in the data that cannot be explained by the model. Another key observation is that the expected value of the error is 0. So the first term in this sum is equal to the variance of the error, and the second term collapses to 0. The rest of the derivation should be straightforward, using the properties of expected value and variance from exam P, so we won't go through the step-by-step derivation here. Let's visualize how bias, variance, and error relate to model complexity through a graph. Here, the x-axis represents model complexity, ranging from simple models on the left to complex models on the right. First, we have the irreducible error. This is the noise in the data that cannot be explained by any model. It remains constant regardless of model complexity because it's independent of the model's ability to fit the data. Next, we have the bias squared. It starts relatively high and decreases gradually as model complexity increases. This indicates that simpler models have high bias, meaning they don't capture the underlying patterns well. When a model is too simple, it underfits the data. Now let's look at variance. It starts low and increases with model complexity. This suggests that more complex models are sensitive to fluctuations in the training data, leading to high variance. When a model is too complex, it overfits the training data. Finally, the expected test MSE is the sum of bias squared, variance, and irreducible error. Notice it exhibits a U-shaped curve. The minimum point of this U-shaped curve indicates the optimal model complexity, where the sum of bias and variance is minimized. This is the essence of the bias-variance trade-off. Our goal is to find the model complexity that minimizes the total error, balancing between underfitting and overfitting. On the left, we have the underfitting region, where models are too simple. On the right, we have the overfitting region, where models are too complex. The sweet spot lies somewhere in between. Understanding this trade-off is crucial for selecting the right model complexity in statistical learning. Another way to visualize the bias-variance trade-off is with a bullseye analogy. This isn't on the exam SRM syllabus or anything, but I think it's a good way to understand the concept in a different way. Imagine the dead center of the target is the value we want to predict. The blue X's represent our model's predictions. There are essentially 4 possible realities the model can live in. In the top left, we have low bias and low variance. All X's are tightly clustered right in the bullseye. This is the ideal scenario. Next, moving down, we have high bias and low variance. The shots are super consistent, just consistently incorrect. This is classic underfitting. In the top right, we have low bias and high variance. On average, the shots are rightish, but each shot is different. This is a pattern I'm very familiar with when I play darts. And finally, in the bottom right, is high bias and high variance. It's inaccurate and inconsistent, which is both bad and embarrassing. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.